Good day to all of you. Today we shall discuss on model question paper set 2 of the subject Digital Design and Computer Organization with the subject code BCS302. In that question number 3A, this belongs to module 2. So explain data flow modeling in Verilog with an example program. 6 marks. There are 3 models in Verilog, that is structural model, data flow model and behavioral model. So out of 3 they have asked one to explain data flow modeling in Verilog with an example program. Okay, the solution: example program in Verilog for implementation we are taking y equal to a logically ANDed with b, logically ORed with c, logically ANDed with d. So in Verilog, while writing the program, we write between module and end module. These are the reserved words. This is start of program, end of program. Simple underscore circuit, that we have given the name to this Verilog program. In bracket, set of all inputs and outputs we'll have to write. So y is the output we are going to take. A, B, C, D are the inputs. So semicolon here. This is the statement which indicates the start of program with its name and set of inputs and outputs in that program. And inside input A, B, C, D semicolon, this declares A, B, C, D as inputs, and here y is declared as output. So this is processing statement, that is, this implements this functionality. So here assign is the reserved word and operators are used in data flow modeling. Assign y equal to a logically ANDed with b within brackets, then here c logically ANDed with d within brackets, both are logically ORed. So this pipeline operator is the symbol for logically ORing. This ampersand operator is for logical AND. Okay, so this statement implements y equal to AB plus CD in data flow modeling. So for this Verilog program, we'll have to give or write the test bench. In the test bench, because this is having 4 inputs, we can write 2 raised to 4, that is 16 input combinations to check this y equal to AB or CD, right? So this is the test bench program. Then this test bench program also will be written between module and end module. So module simple underscore TB semicolon. So this test bench module name we have given as simple underscore TB. When we create this in Xilinx software, it will take a set of inputs and outputs. So when we link with this with the above simple circuit module. So here initial begin, so that software only give first combination of inputs A, B, C, D all are equal to 0. Then this hash 100 semicolon indicates 100 nanoseconds delay is given after giving this input to realize or to wait till getting the out. Where add stimulus comment is here, there will start, we'll have to type our remaining 15 input combinations for ABCD. A equal to 0, B equal to 0, C equal to 0, D equal to 0 with semicolon. Every line is a statement here, hash 100 semicolon. This is the second set of inputs. So like this till 1, 1, 1. So starting from 0, 0, 0 to next 0, 0, 1, 0, 1, 0, 1, 0, like that till 1, 1, 1. We have to type all inputs here. So end of inputs, end of test bench module. So when we run this test bench along with the simple circuit module, we get the timing diagram for y equal to ABCD for different y equal to AB plus CD for different 16 combinations of input. So data flow modeling uses reserved word, assign and operators. Here to implement y equal to AB plus CD, assign y equal to in bracket A ANDed with B, logical operator in bracket C ANDed with D semicolon. This statement is written. A, B, C, D are inputs, y is the output, and Ampersand is the logical AND operator. This pipeline operator is logical OR operator. Assign, reserved word, assigns expression to output Y. Test bench gives input to module, simple circuit here that implements Y equal to AB plus CD. It is another module wherein we give all possible 15 out of total 16 inputs combinations under add stimulus here. A equal to 0, B, C, D equal to 0 and hash 100 semicolon already given by the software, that is Xilinx. When executed, all 16 input combinations of inputs and corresponding Y output waveform we can observe. So that is what is the answer for explain data flow modeling in Verilog with an example program. And here we have taken the example Y equal to AB plus CD. Okay. So that completes question number 3A solution. So next question number 3B, design a full adder and subtractor circuit. 6 marks. Solution. Full adder is a combinational circuit that does addition of 3 binary bits. So first we shall see about full adder and then full subtractor. Okay. Solution. Full adder is a combinational circuit that does addition of 3 binary bits. Let X, Y, Z be the 3 inputs. S for sum and C for carry be the outputs. So this is the truth table for full adder. X, Y, Z are the 3 inputs. C for carry and S for sum. These are the 2 outputs. So 3 input combinations means 2 raised to 3, 8 combinations will be there. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So 8 different combinations for the inputs X, Y, Z are taken here. Then when they are added, when the 3 bits are added, 0 plus 0 plus 0, the sum bit S is 0, carry is also 0. 0 plus 0 plus 1, it is 1. S is 1, there is no carry, 0. Similarly here, S is 1, there is no carry. But when 0 plus 1 plus 1, it is 2. 2 in binary, it is 1, 0. Hence 0 is taken as S bit, carry bit, that is C is 1. Then next case, here also 1 plus 0 plus 0, that is 1. So 1 for S, 0 for carry. 1, 0, 1 when they are added, 1 plus 0 plus 1, so that is 2. So here 1, 0. 0 for sum bit S, 1 for carry bit C. So 1 plus 0 again 2. In binary it is 1, 0. 0 for sum bit S, 1 for carry bit C. But when all the 3 are 1, 1 plus 1 it is 3. 3 in binary it is 1 and 1. So this one is given for sum bit S, this one is given for carry bit C. So this is how truth table for full adder is written. After writing this, there are 2 outputs, 2 kmaps we have to draw. Because there are 3 inputs, 2 raised to 3, 8 squares will have to draw in each kmap. This is the kmap for sum bit S. This is the kmap for carry bit C. So after drawing 8 squares here, X input is written here, YZ inputs are written here. X may be 0 or 1. Here also X may be 0 or 1. So YZ may be 0, 0, 0, 1, 1, 0 or 1, 1. Here also YZ combinations are written. After that here when this is kmap for S, seeing to S column to whichever minterm that is 1, that is filled here. So which minterm is this? 0, 0, 1 means in decimal 1. So this is minterm 1. So for minterm 1, output is 1. So hence M0, M1. Output is 1. That is why 1 is filled. For minterm 2, output is 1. So this is a minterm 2 place. So 1 is filled. This is minterm 4. So output is 1. So this is minterm 4 place. 1 is written. So minterm 7, the output is 1, that sum output, hence in sum kmap, minterm 7 place is filled with 1. So here for minterms 1, 2, 4, 7, the output, S output is 1, hence in kmap, in those minterm places, logic 1 is filled. So after filling, grouping must be done. Nowhere octet or quad or even pair is not possible. Diagonally we cannot pair. Okay, the shape should be either square or rectangle. So each form individual groups. So with respect to this group, we can write row wise x, column wise y dash, z dash. So that is what is written here. For this row wise x dash, column wise y dash, z. So that is what is written here. For this group, row wise x, column wise y, z. So x, y, z is written. Or for this group, row wise x dash, column wise y, z dash. So that is what is written. So then for each group, what row wise and column wise we find common. So using all the terms with plus sign in between, we write simplified S expression. So S equal to x y dash z dash plus x dash y dash z plus x y z plus x dash y z dash. So kmap for C, if you consider this is the column C output, this is 0, 1, 1 means min term 3, this is min term 5, 1, 0, 1 means 5, min term 5, 1, 1, 0 means min term 6, min term 7. So for min term 3 it is 1, then min term 5, 6, 7, carry output is 1. So 3, 5, 6, 7. So min term 0, 1, 2, 3 place. We had to fill 1, 5, 6, 7. 4 is not there. 5, 6, 7. 3, 5, 6, 7. In those min terms places, because carry is 1, we have to fill logic 1 here. After filling, we have to group. These two form one pair. These two form one pair. These two form one pair. There are 3 groups. So this group, if you take 1, 1 are the 2 members here, they are covered in this row where x is 1, hence x. Okay, then these two are covered in these 2 columns 0, 1, 1, 1. So second one with respect to z is common, so z. So xz for this group. So next for this pair, these 2 members are covered in these 2 rows. Here x0, x1. So row wise nothing is common, but column wise 1, 1 that corresponds to yz. So that is why yz. So this xz for this group, yz for this yellow group. Next for third pair, these 2 ones they are covered in this row. So x is 1 that is taken here. Okay. Then here these 2 ones they are covered in these 2 columns. So 1, 1, 1, 0. First one with respect to y that is common, hence y. Hence C equal to xy odd with yz odd with xz. So this is the simplified expression for C which is taken from the C column in the truth table. Now we have to write the circuit diagrams for this. Okay, logic diagrams. So what we can draw? So x ANDed with y dash ANDed with z dash. This is 3 input AND gate. Like that these 1, 2, 3, 4. 4 3 input AND gates we should draw. Then the outputs of OR logically ORed. Hence 1, 2, 3, 4. 1 4 input OR gate is required. Here this is the expression for C. X ANDed with y, y ANDed with z, x ANDed with z means 3 2 input AND gates are required and all should be logically ORed. So 1, 2, 3. So 1 3 input OR gate is required. So this is the logic diagram for S output. Okay. So from truth table for S output using kmap we had derived the simplified expression for S that we have written here. According to this logic diagram is drawn. S equal to x y dash z dash. So x y dash z dash they are ANDed. So here x y dash z dash we get. Similarly here x dash y dash z and here x y z and here x dash y z dash. So those product terms are here. All are logically ORed. So to implement this yes, we need what logic diagram we have drawn here? 4 3 input AND gates and 1 4 input OR gate. So this is what is logic diagram for sum bit, that is S bit. Okay. So this is the logic diagram for carry bit. So carry is found to be xy plus yz plus xz. So from truth table and then from kmap, this is what the simplified expression for carry we had got, that carry bit C here. So according to this, x ANDed with y, so one AND gate, x ANDed with y we get here, similarly y ANDed with z here, and similarly x ANDed with z. So all the three, they are logically ORed. So hence 3 2 input AND gates and 1 3 input OR gate is required to implement the carry bit C for the full adder. So this is the logic diagram for the full adder carry bit C. So similarly, next we shall see for full subtractor. So this is the truth table for full subtractor. X, Y, Z are the 3 inputs. Borrow, difference are the 2 outputs. So for 3 inputs, 8 possible input combinations from 0, 0, 0 to 1, 1, 1 are written here. So if you observe the difference bit and sum bit, both are one and the same. So difference, how it is found? 0 minus 0 minus 0, that is 0. 0 minus 0 minus 1. So in 0 we cannot subtract 1. So we take a borrow, that is 1 here. When we take a borrow, it is equivalent to 2. So 2 minus 1 is 1, that we have written here. Okay. So next 0 minus 1 minus 0. So 0 minus 1 we cannot do. We take a borrow, it is 2. 2 minus 1 is 1, that is what we have written here. 0 minus 1 we cannot do. We take a borrow, equivalent to 2, it is 2 minus 1 is 1. 1 minus 1 is 0. So difference is 0. So 1 minus 0 is 1. 1 minus 0 is 1. So the difference answer is 1. We have not taken borrow, hence it is 0. So 1 minus 0 is 1. 1 minus 1 is 0, hence difference is 0. Borrow also not taken, hence it is 0. 1 minus 1, it is 0. 0 minus 0, it is 0, hence difference is 0. Borrow also not taken, that is 0. 1 minus 1 is 0. 0 minus 1 we cannot do. So borrow we have taken, it is equivalent to 2. 2 minus 1 is 1. Hence both are 1 and 1 here. Okay. This is how the output columns are filled for full subtractor. After that, if you observe D column and S column, hence they are same. So K maps will be same, their expressions will be same. This is expression for sum and this is the expression for difference here. Both will be same and circuit diagram also will be same. But K map for B, if you take here, B is found to be 1 for 0, 0, 1 means minterm 1. 0, 1, 0 means minterm 2. Then 0, 1, 1 means minterm 3. So 1, 2, 3. Then last one 1, 1, 1, 7. So borrow is found to be true or logic 1 for 1, then 2, 3 and 7. Hence in minterm 1, 2, 3 and 7 place it is filled 1. Next, when simplified, this is one pair, this is another pair, this is third pair. So 3 pairs we can recognize here. So for this pair, row wise 0 is common, that is x dash, and column wise this one is common, that is z, that is x dash z for this group. Next, for this pair, row wise x is 0, x dash, column wise this one which corresponds to y, hence x dash y is common. So for this second group. For third group, row wise nothing is common because x is 0 here and 1 here. And for this group, column wise 1, 1 is common which corresponds to yz, hence yz. Hence there is difference in borrow expression here when compared to carry. Sum expression and difference expression were same, but for carry and B there is different. So carry was found to be xy plus yz plus xz. But here borrow is found to be x dash z plus x dash y plus yz. Hence the circuit for this will be different. Same as this 3 2 input AND gates we draw. one 3 input OR gate we draw, but the inputs for this is x dash z, here second one x dash y, third one yz. Their inputs were different. Okay, so this is the logic diagram for difference bit. So one AND gate, 3 input AND gate. So x, y dash, z dash, those inputs are given. Here we get x, y dash, z dash. Similarly here x dash, y dash, z. Similarly here x, y, z. Here x dash, y, z dash with corresponding inputs at AND gate. So all are logically ORed. Hence we get here D equal to this expression. That is what is implemented by this logic circuit. So this is the logic diagram for difference bit, that is D. This is the logic diagram for borrow bit, which is equal to x dash z plus x dash y plus yz. So x dash ANDed with z. So that is here x dash and z are ANDed. So x dash z we get here. Similarly x dash y here. Similarly yz here. All are logically ORed. Then we get borrow bit as this. Okay, so for this we need 3 2 input AND gates and 1 OR gate. 3 input OR gate, similar to carry bit of full adder, but the inputs do vary. Okay, so that completes the solution of question number 3b, designing of a full adder and subtractor, which was asked for 6 marks. So that completes question number 3b, design a full adder and subtractor circuit, asked for 6 marks. Okay, so next question number 3c, design an octal to binary encoder, 8 marks. So octal to binary encoder designing means we have to derive the equation for the outputs and draw the logic diagram. Solution, octal to binary encoder has 8 inputs and 3 outputs. The 8 inputs are D7, D6, D5, D4, D3, D2, D1, D0. And 3 outputs, let them be X, Y, Z. The truth table of octal to binary encoder is as follows. 8 inputs are listed here. D0, D7, D5, D4, D3, D2, D1, D0. Here 3 outputs are listed X, Y, Z. So at any time octal input means out of 8 bits, any one bit will be 1. So on input side D0 is 1. And on output side X, Y, Z all will be 0. This is the encoded output of the input. D0 is 1. Here decimal, this is 0. So binary combination of 0 is 0, 0, 0. So this binary combination 0, 0, 0 represents 0. Hence on the input side D0 is 1. So this is octal to binary encoding. So next octal is D1 is 1. Only that will be 1. So 0, 0, 1. At the output side 0, 0, 1 will come. So next D2 is 1. Only D2 is 1. So binary encoding of 2 means 0, 1, 0. So X, Y, Z output will be 0, 1, 0. Then D3 is 1. So 3 with 3 bits means 0, 1, 1. Hence binary encoded output of octal input D3, that is equal to 0, 1, 1. In case of when D4 is 1, here 1, 0, 0. When D5 is 1, 1, 0, 1. When D6 is 1, 1, 1, 0. When D7 is 1, 1, 1, 1. Thus the output will be encoding of binary encoding of this octal input. Octal input means out of 8 inputs any one will be logic 1, which is 1 that in binary encoded version output will be given in the form of X, Y, Z. So if you observe this truth table, X is 1 for D4 or D5 or D6 or D7. So X expression we can write as X equal to D4 plus D5 plus D6 plus D7. X is, this output is 1 for when D4 or D5 or D6 or D7 is 1. That is what is the expression here. Similarly, Y, if you take that Y output is 1 for D2 or D3 or D6 or D7. Hence Y equal to D2 or D3 or D6 or D7. Next, Z output, if you consider, this is 1 for D1, D3, D5, D7. So Z is 1 for D1 or D3 or D5 or D7. Hence Z is equal to D1 or D3 or D5 or D7. So seeing to these expressions or Boolean equations that are derived for X and Y and Z from the truth table, we'll have to draw the logic circuit for octal to binary encoder. So here all the inputs are shown: D0, D1, D2, D3, D4, D5, D6, D7. X is equal to D4 or D5 or D6 or D7 means from D4, D5, D6, D7 inputs are taken. So that gives X output. Similarly, Y for D2. So this is D2, this is D3, this is D6, D7. From their inputs are taken. The output of that OR gate gives Y equal to D2 or D3 or D6 or D7. So similarly, Z, for that D1, D3, D5, D7 inputs are taken. They are logically ORed. Hence the output is Z equal to D1 or D3 or D5 or D7. So this is the logic diagram for octal to binary encoder. So that completes the solution of 3C. So with this we come to the end of the discussion of question number 3 ABC for a total of 20 marks. Okay. I hope you understood. Thank you.